In this video, students will observe experiment number 7, which is about a magnetic field and an electromotive force. We begin with a short history and basic concepts of this experiment. A compass needle is known to align parallel to the local magnetic field. The reason is that the needle itself is a magnet, and its alignment along the magnetic field minimizes the net torque from the magnetic field. We can use a compass to identify the direction of the magnetic field at any particular place. In 1820, Hans Christian Ørsted, a Danish physicist, discovered that electricity and magnetism are not two independent subjects. In one evening, Ørsted placed a compass close to a wire. The wire was straight in the north-south position. He placed a compass under the wire. Initially, there is no current in the wire, the compass points north. After he allowed the electric current on the wire, the compass responded to the current in that wire and it no longer pointed north. The picture here shows a simple drawing of such an experiment done by Ørsted. When there is an electric current in the wire, the compass responds to the electric current. From more experiments, Ørsted discovered that an electric current produces a magnetic field, surrounding the current in the direction perpendicular to the direction the current, and also perpendicular to the radial direction from the wire. The picture here shows the direction of the magnetic field and the electric current. In vector calculus, we can identify the normal vector of the surface by using the right-hand rule. The right thumb points in the direction of the normal vector. The other fingers curl along the curve on the surface. We can apply this rule to the case of an electric current and a magnetic field. By applying the right-hand rule for this case, the thumb points in the electric current direction, and the other fingers curl along the magnetic field lines. These fingers give the direction of the magnetic field. While an electric current creates a magnetic field can also create an electric current. 14 years later, Lenz proposed that changing magnetic flux can induce a current. Suppose there is a changing magnetic field inside a wire loop. In that case, an electric current will be created such that the magnetic field created by this induced current opposes the initial changing magnetic field. The figure here shows that if you move a magnet in and out of a coil, the changing in magnetic flux inside the coil will induce an electromotive force to induce a current inside the wire. In this experiment, you will observe how a magnetic field is created by an electric current, and how a changing magnetic field induces an electric current in a wire loop. You can also measure the electromotive force by just using the simple formula here. Epsilon is the electromotive force. I is the electric current in the circuit, and R is the total resistance in the circuit.